Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our 5 things you need to know playlist. And in this episode, it's about pressure transient analysis, and it's going to be very interesting. All right, so here we go. The first important thing. All right, we know Wellbore storage and the order of magnitude of Wellbore storage. In this case for gas well, you can see in this table. Okay, so we have very high Wellbore storage coefficient if the value is greater than 10 meter cube per megapascal. And we can read it together. Wellbore structure and test procedure in this condition. Usually we find in wells which are extremely deep, okay, and then normal or fairly low formation pressure and surface shut-in. So if we perform surface shut-in, usually we find very high Wellbore storage. And high Wellbore storage, if the value between 1 through 10, again, meter cube per megapascal, and we find it in deep gas wells, wells with normal formation pressure, and again, surface shut-in. Okay, so if you use surface shut-in, if you shut in your well using surface valve, don't be surprised if you get, high or very high Wellbore storage. And medium Wellbore storage coefficient, 0.1 to 1, we find it in shallow gas wells or deep gas wells with super high formation pressure and again, surface shut-in. But if we use downhole shut-in, we can have low Wellbore storage coefficient, which is good because Wellbore storage usually mask the most important flow regime in our pressure transient analysis. All right, and the second thing is this one. It's quite long, but it's very important. So we have Stegemer and Matthews in 1958 reported that 75% of the wells in oil field in South Texas exhibited an unusual pressure response during pressure buildup, where the pressure would rise to a maximum and then decline before reaching a stabilized reservoir pressure. Okay, so the pressure will rise to a maximum value and then it declines. Okay, redistribution of phases causes an increase in pressure at both the top and bottom of the wellbore. Okay, so in pressure transient analysis topic, we usually call it pressure hump. Okay, pressure hump. So 75% of wells in South Texas, okay, in oil field in South Texas, usually exhibit again the pressure hump during the well testing. Okay, why? It's because redistribution of phases, which caused increase in both the top and the bottom of the wellbore. So here we have PT and we have PB. It's the top pressure and bottom hole pressure. Originally, the condition is like this, and then we shut in the well. So we have the new condition. It's the new top pressure and the new bottom pressure. And after we shut in, the phase will be redistributed, okay? And the redistribution of phases causes increase in both the pressure, PT and PB. So initially, PT is here, okay? And PB is here. But after the phase redistribution, now we have new PT is the initial PT plus a positive value, which means that new PT is greater than the initial PT. And the new bottom hole pressure is the initial bottom hole pressure plus something positive value. which means the new bottom hole pressure is greater than the initial bottom hole pressure. And during the evaluation, we usually find it as pressure hump. So that's the second very important thing you need to know in pressure transient analysis topic. And the third one, okay, let's see. There you go. This is the pressure hump. All right. Pressure hump due to phase segregation or phase redistribution, you name it. Okay. This pressure hump causes a temporary reversal of flow into the formation. So previously we understand why the pressure increase. It's because phase redistribution or phase segregation, and we have pressure hump. This is the next thing that is very important for us to know. The pressure hump causes temporary reversal of flow. Okay, so there will be reflux from the wellbore into the reservoir, back into the formation, back into the reservoir. Why? Because the pressure inside the wellbore is a little bit greater than the pressure in the reservoir. So there will be reverse flow from wellbore into the formation. There will be reflux, okay, because of this pressure hump. That's the third one. The next one, here you go. All right. Okay. All right. A new well often cleans up during early production as completion fluids and or mud filtrate is produced from the near wellbore region. Okay, so if we have new well, don't be surprised. We usually have cleanup during early production. Okay, why? Because the completion fluid or maybe the mud filtrate can be potentially produced back from the near wellbore area, produced by the well, and yeah, we get rid of that completion fluid and the mud filtrate. Okay, so the well is cleaning itself. This cleanup phenomenon may result in decreasing time-dependent skin factor. Okay, because we have cleanup, we will have decreasing skin. And skin in this case is time-dependent. So we will have decreasing time-dependent skin. Okay, this is the information. And the picture is like this. So if we perform pressure transient analysis, we will have the bottom hole pressure profile. And usually we will find like this one. Okay, so the pressure first go as low as this value. And for a little while, it will increase and then stabilize. Pressure increase means the skin decreases, and the skin decreases here because it's a time-dependent skin. The skin decreases because the cleanup. All right, so it's time-dependent skin. It's not a constant skin, it's changing skin. It's time-dependent skin, and it decreases because of the cleanup process. All right, during the early production. All right, the last one. Okay. All right. So movement of a gas-liquid interface in the wellbore can cause a time-dependent pressure offset between the pressure at the perforation, which we are trying to measure, and the pressure actually recorded by the gauges. Okay, so again, previously, before we have phase redistribution, phase segregation. Here we have movement of gas-liquid interface inside the wellbore. Okay, here we have our gauges. We use tandem pressure gauges, and we have pressure. The most important thing is here, PWF, the pressure at the perforation interval. But what we measure is actually the pressure at the gauge. Okay, so here you have the interface between gas and liquid moving up from point A, B, C, D, the interface move up. All right. And at some point, the interface passes through both gauges. Initially in point C, the interface passes through the lower gauge, and at point D, the interface passes the upper gauge. Okay, so the movement of gas-liquid interface in the wellbore, it can cause time-dependent pressure offset between the pressure at the perforation and of course pressure at the gauge, because there will be change in density. Previously, the gauge will be exposed with the density of gas, but after the interface moves up, the gauge will be exposed with the density of liquid. So there will be time-dependent pressure offset, okay? And according to Matar estimates that approximately 3/4 of tests on wells flowing a mixture of gas and liquid exhibit this behavior. Okay, so the majority of well tests will show mixture of gas liquid, yeah, the mixture of gas and liquid, and it will exhibit this behavior. So the interface will be moving, okay, it will move up, and this is the result. So if you have moving gas liquid interface, you will have something like this. You will have the derivative increases and then decreases again. So at point A, gas liquid interface moving up, but at point B, gas liquid interface moving downward. In the left figure, we have this picture because we use smoothing factor of 0.1, but without smoothing, we have this one. Okay, and of course, it will disturb our evaluation, our interpretation. It's not a reservoir factor, it's a wellbore factor because it's gas liquid interface moving upward and downward. All right, so be careful if you have multi-phase flow, you will have gas and liquid flow. Most likely you will have gas liquid interface moving upward and downward during the well test, during the shut-in. All right. So yeah, did you know those 5 things before? See you on the next 5 things you need to know in petroleum engineering. Thank you.